Hello friends, this is Vatsala Singh, roll number 2015 BIT 051, and today I'll be explaining you Dijkstra's algorithm, which is a shortest path algorithm. Dijkstra's algorithm was given by computer scientist Edward Dijkstra in 1956. It is a shortest path algorithm widely used in network routing protocols, most notably OSPF, that is, Open Shortest Path First. If the efficiency of a network is present, it completely depends on the algorithm used for giving the information to the routers and further processing the data. Routing is one of the most important features in today's network, and so this algorithm plays a major role. It is an optimal routing algorithm to find the shortest path in a weighted link route connecting various routers. So, in a particular route, every router is linked with a weight and a cost is given to it. So, to find the ultimate path, the minimum cost needs to be found out. It is also called a smallest path algorithm for routing. We find the shortest path from a source router A to a destination router B based on the routing cost. Let's take, for example, the given route, in which router 1 can be considered as the source, and we need to find the shortest path with the minimum cost to reach the destination router. Let's consider it to be router number 5. Over here, as you can see, router 1, 2 are given a weight of 4. That is, the link cost is 4. Router 1, 4 are connected by 8. Router 2, 3 are connected by a weight of 3. Router 3, 4 are connected by a weight of 4, while router 4 and 5 are connected by a weight of 7. So let's begin by finding the shortest path. There are a few major steps in this algorithm. To begin with, step 1. You need to assign every router a tentative distance. Here, the tentative distance refers the distance required by the router with the cost to move from one router to the other. So let's consider the source. To move through the source will always take a value of 0, while all other networks will be infinite. So as you can see, we always give the source a value of 0. Here, the source router being 1 gets a value of 0, while 2, 3, 4 and destination router 5 get a value of infinity. Step 2. Set source router as current node and mark all others as unvisited and start to fill the routing table. Herein, source router is considered a node while all other nodes are marked as unvisited and started to fill the routing table. Routing table consists of various entries, which we'll be seeing further. Step 3. For a current node, consider that it is a router. Consider all unvisited nodes and calculate the distance. Compare current distance with the calculated distance and assign a smaller value. As we need to find the shortest path with the minimum value, we consider the smaller value of the two. We'll learn it through the further example. So, the entries in the router table are the entry of the router, the path value, and the distance between the routers, that is the cost value, which can be considered as a path matrix and a cost matrix while we develop the C code. To begin with, here, as we have earlier mentioned in step 1, we have given the same values here. As you can see, number is the step number, entry is the router entry, considering the first to be the source. C is the cost, while in bracket the number is the number of the router, that is the name of the router. So the cost required to move from the entered router to this particular router is mentioned over here. Moving further, in step 1 we have given the values as it is. Let's come further. Step 2. So let's see the first path. To move from router 1 to 2, the value is 4 as there is a direct connection. To move from router 1 to 3, we need a connection which is not possible directly over here, as to 1 to 3 we don't have a direct route. While for router 1 to 4, the value is 8. While for the router 1 to 5, the value still remains infinity because it is not yet defined. The minimum of the two is 4. So the next entry into the table is of router number 2. So here, again for 1 to 2, the minimum cost is 4 and the shortest path remains 1, 2. While for the next one, that is router number 3, the minimum cost is added because we get it through the path 1, 2, 3, and the cost is 4 plus 3, that is 7. For router 1, 4, we yet have another path, that is 1, 2, 3, 4, which accounts to a value of 11, while directly from 1, 4, we have a value of 8. So we get the minimum value, that is, as we mentioned in step 3, the smaller value of the two, which is 8. Now let's come to router number 5. The first path is available right now, that is 1 to 2, 3, 4 and 5. Here as we can see, the value accounts to 4 plus 3 plus 4 plus 7, that is a value of 18 units. The path is 1, 2, 3, 4, 5 as mentioned in the table. Moving further, router 3 gets its entry into the entry column as it has a value of 7, which is minimum next. Router 1, 2 are yet fixed with a value of 4. Router 1, 3 are yet fixed with a value of 7 and the same path. Router 1, 4 has a direct connection as mentioned in step 1 with a value of 8. And router 1, 5 yet has a connection of 1, 2, 3, 4, 5 with a value of 18 units. But is there a possibility of getting a smaller value? It might be, so the next entry may change the values. Router 4 gets its entry into the table. So the value is 4 for router 1, 2, 7 for router 1, 2, 3, 8 for router 1, 4. But as you can see, the value for router 5 changes because now we have a path available directly to router number 4, that is 1, 4, 5, which gives a value of 15, that is 8 plus 7. Now we have two particular options. First one, router 1, 4, 5 with a value of 15, and the second one, router 1, 2, 3, 4, 5 with a value of 18 units. And as according to the algorithm, we use step 3 giving the smaller value entry into the table, that is 15 units. Let's go to router number 5 as the next entry. As we can see, the values do not alter further. They remain the same because these are the shortest values possible, which is the smaller ones of the maximum possible. And the final values remain 4 for router 1, 2, 7 for router 1, 2, 3, 8 for router 1, 4, and 15 for router 1, 4, 5. And ultimately, we have reached from the source router to the destination router with a value of 15. Well, let's see, are the steps of the algorithm complete? Step 4 says that when all nodes are visited along with the destination node, end the traversal. And as you can see in our entry column, we have all the 5 nodes along with the destination node 5. So step 4 is complete. And we can stop, that is end our algorithm here. And ultimately, we have found our shortest path along with the minimum value possible. Thus, the minimum distance path out of the options present is 1, 4, 5 with a cost of 15 units. And we have effectively used Dijkstra's algorithm accordingly to find the shortest route. As we know, in day-to-day networks, we have long routes, but this example was quite a similar one. Thank you.